Hello everyone, hello sir. My name is Pranab Nandi. I am MTech CSC second semester student. Today my seminar topic is walkthrough of PIQ discipline implementation in NS3. So when I see the PIQ discipline algorithms, it is present in the traffic control module of NS3. Here we have two files, one is .h files and one is .cc file. The .h file basically give the brief overview of the class, and actual implementation of every single method is there in the .cc file. Here the PIE stand for the proportional integral enhanced queue discipline algorithm. It works on the concept of queue delay on the in queue time, and it actually adopts the PI controller concept to control the latency. To implement the PIQ discipline algorithms in NS3, it creates a class of PIQ discipline which inherits the Q discipline class. It has several methods, out of which some of the popular methods are the do in queue methods. When a item or the packet is entering to the queue, it calls the do in queue function. It decides whether to keep the packet or to drop the packet. For that, it take the help of the drop early function. This drop early function returns true if we need to drop the packet, or it returns false to enqueue the packet. There is another function called calculate p, where it calculates the drop probability periodically over a certain interval, and the do dequeue function is called when a packet is dequeued. At the same time, it calculates the average dequeue rate, which is useful for calculating the current queue delay. Apart from several methods, it has several member variables, and out of which approximately 28 member variables are there. And the first part is the member variables which are supplied by the user, and the second parts are those member variables which are maintained by the PIE. Out of these many member variables, the some more important member variables are T updates. It is the time period after which the PIE function calculates the drop probability. The queue delay reference, it is the desired queue delay. The mean packet size, what happened in real world, the router used to receive packets of different size, but for NS3, for the simulation purpose, we consider an average packet size for every packets, and for that we have to use the mean packet size. Also some tuning parameters like alpha and beta, which is useful for the calculation of these are the constant basically to calculation for the drop probability. Apart from that, we have some variables maintained by PIE, like drop probability of the PIE algorithm, the old queue delay, and then current queue delay. The burst allowances means the amount of time we can allow burst before and the drop early function kicks in. Also the average dequeue rate, which is useful for calculating the current queue delay, and in measurement, which is helpful to calculate the drop probability if we are in the measurement cycle. Not drop probability, to in measurements is useful to calculate the average dequeue rate when we are in the measurement cycle. And apart from that, one most important thing is the mActive function, mActive variable. Basically the mActive variable is indicator that whether the PIE algorithm is turned on or off. If it is initially off, then with the help of this threshold, if queue delay cross this active threshold value, then we activate the PIE algorithm. If the queue remains idle for a certain amount of time and the drop probability is 0, and the queue delay and the old queue delay is also, we all deactivate the PIE algorithm for the amount of for some certain amount of time. Now let's see the actual implementation of all these functions. The first part of the code includes the add attribute. These are the variables supplied by the users. If user don't provide these variables, it will take the by default value, like mean packet size will take 1000 bytes, then the alpha beta value, then T update value, then max size, the maximum number of packets accepted by the queue discipline. And apart from that, it has like usage scene. If true, then packets can be marked instead of being dropped. Also it has marquee sense threshold value to compare it with the drop probability, and also it has some like active threshold um, to decide when to activate the PIE algorithms. So first part contains the constructor of PIE algorithms. It just basically create an object of the uniform random variables. Here we use the uniform random variables because here the probability of generating any numbers is uniformly distributed, and also it triggered the Artioris event, the event that is used to decide the time interval of the probability calculation. Then it has the destructors of PIQ discipline class, and then a PIEQ discipline class has do dispose function, which basically defines the the MUV random variables, and then it cancels the Artioris event and also calls the do dispose function of its parent class. Then it has the methods like get Q delay, which basically give the current Q delay of the queue, then assign stream, basically assign the stream to the random variable. Now it comes before do enqueue function. Let's see the initialize parameters. Basically when we deploy the PIEQ discipline algorithms in the routers, it basically disable the aim active, means it set the aim active value as false, means initially the PIE algorithm is disabled, also the measurement cycle is also false, and the rest of the parameters are set the default value. So initially when a packet is enqueued, it it first take the current queue size and add the packet size and checks whether it is greater than the capacity of the queue. If it is greater than the capacity of the queue, simply drop the packet. This time we are dropping the packet because of the buffer full, and this is known as force drop. It is reactive in natures, and suppose if the initially, like for the first packet, it will be false because first packet will not cause the buffer overflow. So in that case what happens, it will enter into the if else if condition. Here we have not activated this condition will become false, and aim active is also false. So as this part is false, the entire condition will be false, then controller will come to this line and it will simply enqueue the function. Then it will check whether the PI is turned on or not. If it is turned off, then it will check if the current QTL is greater than the active threshold, then it will activate the PIQ discipline. Also the measurement cycle will be set to true, and other parameters like drop probability will be 0, DQ count will be 0. We will see every parameters in the in upcoming functions. Now suppose in the for the first packet, it simply enqueue it, and after that it enables the PIE algorithm. For the second packet, it will check, okay, now the PIE algorithm is activated. Now it will call the drop early function to decide whether to drop the packet or not. Suppose it returns true, that the packet needs to be dropped, then it will check one condition, that whether the packet can use the ECN bit or not. It is can use the ECN bit, then whether the packet is marked or not. If it can be marked or it is already marked, then we avoid the dropping, otherwise we simply do the drop. This drop is known as unforced drop. Here we are dropping the packet even before the queue is full. It is known as means it's proactive in natures. And also instead of dropping, if we mark the packet, then this is known as unforced mark. It is also proactive in natures because we are marking the packet even though the queue is not full. And also sometimes if queue is remains idle for a certain amount of time, then it will check if the drop probability is 0, the current queue delay is old queue delay is 0, and also the current queue delay is 0. Then in that case it simply deactivate the PIQ discipline and set the measurement variable also false. Now come to the drop early function. The drop early function, what it does basically, first it checks if the burst tolerances is greater than 0 or not. Means if we can still allow the burst, then we simply skip the drop early concept, simply allow the packet to enter into the queue. But if there is no burst, the bursted is no burst, the convert the bursted into in burst protecting and set the m burst allowances value, and after that we take the drop probability value to the p variables, which is also stand for the probability, take the packet size. Now if we are using the byte mode, then convert the probability according to the packet mode, and after that, before comparing this drop probability value, it checks certain condition, like if the old queue delay value is half of the desired queue delay or the reference queue delay, and the drop probability is greater than, sorry, less than 0.02, simply returns false, means allow the packet to enqueue into the queue. If the queue size, number of packets that is exist in the queue, is less than 2, then also allow the packet to enqueue, so return false. Then another concept comes called de-randomization. uh, if you see, like, what happens, sometimes the PI algorithm drop the packet so frequently, and sometimes it drop the packet so 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 sparsely that create a deviation in the link utilization, also the queue latency. To avoid the condition, it uses the concept of de-randomization, where it accumulated the drop probability, and after that it checks if the accumulated drop probability is less than this threshold, then simply enqueue the packet. If it is greater than this threshold, then simply drop the packet. If it is in between these two, then only we will check for whether to drop the packet or not based on the drop probability value. And it does the same thing. It accumulated the drop probability, then it checks if it is less than 0.85, simply returns false, means allow the packet to enter into the queue. If it is greater than 8.5, then simply returns true, and drop the packet. Else it checks the drop probability value with the against the uniform random variable. If the uniform random variable is greater than p, then returns false, means allow the packet to enter into the queue. Else return true, means drop the packet. Now let's come to the calculate p function. Basically it calculates the probability over a certain interval period, and the period is defined by this t update time. Every time when it is called, first it checks if the DQ rate estimator is enabled or not. If it is enabled, we use that average DQ rate to calculate the current queue delay. It is calculated by the current queue size and divided by the average DQ rate. We get the queue delay. If the average DQ rate is not greater than 0, then we simply take the current queue delay to 0. If this DQ rate estimator is not enabled, then simply take the current queue delay, which is stored in the member variables mq delay. And after that we check that whether the burst allowances is still there or not. If there are some still burst allowance time is left, then simply we set the drop probability to 0, because the burst can be allowed to enter into the queue. Else we calculate the probability. It is calculated by alpha into current queue delay minus reference queue delay plus beta into current queue delay minus the old queue delay value. After calculating the probability based on the old drop probability value that was there in the previously, we normalize the probability variable p. Now after that we check for the cap drop adjustment. Like it has another concept. In the slow start phase, the packet keep on, if the sender is in the slow start phase, the packets are keep on coming, and in that case what happens, the drop probability values also increases quickly. And because of the high increment of the drop probability, it might create a negative impact on this algorithm. So because of that, we enable the cap adjustment to we enable the cap adjustment so that drop probability increases in a certain way in each step. And it checks, like, if the cap adjustment is enabled, then it simply checks this condition, the m drop probability is greater than 0.01 and the calculated probability is 0.02. Simply set the greater than 0.02, then simply set the probability value to 0.02. Then it adds the calculated probability value with the m drop probability. Now it checks, like, it also exponentially concept of decaying the drop probability. So because of that, it checks, like, if the queue delay is 0 and the old queue delay is also 0, we exponentially decay the drop probability value. And after that, it bounded the drop probability value. If it is less than 0, keep it to 0. If it is greater than 1, keep it to 1. Else simply keep the m drop probability value equal to p, which is the calculated the probability value. Then it simply check whether burst allowance is less than MT update or not. If it is, then set the burst allowances to 0. Else simply subtract it with from the T update, and after that it calculate the burst reset limit, and it checks if the current queue delay is half of the reference queue delay and the old queue delay is half of the reference queue delay, and the drop probability is 0, and also that this missing init flag, which is a local variable, is false or not, like it is defined here, a missing flag. If it is false, simply what it does basically, it simply invalid the DQ count value for during the DQ. Do DQ function it useful for calculating the average DQ rate and average DQ rate to 0. Second condition is that if the Q delay is half of the reference Q delay, old Q delay is half of the reference Q delay, and also the dot probability is equal to 0 and burst allowances is 0. In that case, it changes the burst mode in protecting to in burst protecting mode to in burst mode, in burst mode to no burst mode. After that, it simply stored the current Q delay value to old Q delay value and trigger the TRS event, the event that is used to decide that the interval of drop probability calculation. Then comes to the do DQ function. It basically checks whether if the queue is empty, then simply say queue is empty, otherwise DQ the item, and after that start the start counting the time from now onwards, and then get the packet size of the DQ'd item. It checks if it checks whether the DQ rate estimator is enabled or not. If it is enabled, then it checks whether it is in the measurement cycle or not. For that, if the queue size cross the DQ threshold, and if the measurement cycle is not enabled, simply enable the measurement cycle and initialize the parameters like DQ start and the DQ count. In the next iteration, it checks okay, now the measurement, it is in the measurement cycle, simply keep on counting the packets size which are getting DQ'd, and if the DQ count value crosses the DQ threshold, take the duration for the amount of time it takes to cross the DQ threshold, and if duration is greater than 0, then simply calculate the if the average DQ rate is was 0, then it simply calculate the average DQ rate equal to the amount of bytes it DQ'd and during this duration. So this is the DQ average DQ rate. If the average DQ rate was already calculated some value, then it basically take the average of the old average DQ rate and plus the half of the current calculated DQ rate. And again it checks it still it is in the measurement cycle, then again keep on entering into the measurement cycle to update the average DQ rate. If this condition falls, when the Q size is less than DQ less than equal to the DQ threshold, then simply disable the measurement cycle, come out from the state. If the that DQ rate estimator was false, then they come to this condition which manually counts the Q delay, where it will calculate the now value when it was triggered, when we DQ'd the packet. Here the when we DQ'd the packet, then we started calculating the holding the storing the count time in the now variables, and now this is the current timestamp. Or if the and also if the queue is empty, like everything packets is there in the queue, then simply set the queue delay value to 0 and return that item. The check configuration function basically check the configuration whether the in packet filter is greater than 0 or not, and then it will say it cannot have any, it returns an error like cannot have any packet filter. If there is no internal queue, it simply add an internal queue with the size of the queue is a max size, which is by default is 25 packets. Also it checks if the internal queue successfully created or not, otherwise it will say like it needs one internal queue. So this is the overall algorithm of PI controller. Thank you.